Today we're going from the magnetic vector potential to the radiation integral. So we'll talk about mathematically how to get from here to there, and once we get to the radiation integral, we'll talk about some of the features of it and what it means and what's happening physically in there. So let's start by reviewing what exactly is the magnetic vector potential, specifically for time harmonic scenarios. All right, we start by knowing that there's no divergence of the magnetic field. We also know for any vector field, let's name it A, the divergence of the curl of any vector field is 0. So does that mean that the magnetic flux density, B, is the curl of something? It sure can be. Why not? Let's say it is. In that case, we can say the magnetic flux density is the curl of some vector field A, and we're going to name that the magnetic vector potential. You can also write this in terms of H, in which case H would just be 1 over mu times the curl of A. This does not fully define A. Because in order to fully specify a vector field, you need to both have its curl and its divergence. We're going to leave that for now, but it's important to know that we need to define the divergence of A, and that really we can define that however we want, because right now we only have a constraint on what the curl of A is. So we can choose the divergence of this vector field A to also be some value that's useful to us. But let's not start there. Let's start moving towards a wave equation and see what divergence is going to be the most useful thing to put in for A. So we'll start with Ampere's law. The curl of H is J, the volume current density, plus J omega epsilon E. That's the time derivative of the electric flux density. So if we put in our earlier equation for A in terms of H, we can write this as the curl of A is mu J plus J omega mu epsilon E. Okay, cool. We're going to make use of a vector identity now to turn curl A into the gradient of the divergence of A minus the Laplacian of A. And we keep the right-hand side the same. Mu J plus J omega epsilon mu E. All right. We'd really like to have A just in terms of J and not depending on the electric field. We'd like to have just a relationship between A and J, and that's going to be our inhomogeneous wave equation for how we figure out what all of the fields do to some current source that's radiating. All right? So how are we going to deal with the electric field? We're going to start with Faraday's law. Remember, Faraday's law is that the curl of E is minus J omega mu H, which is also minus J omega curl of A. All right. Well then, what if we move both of these things to the same side? Then we can write, if we move both of these terms to the same side, we could write that the curl of E plus j omega A is equal to 0. What sorts of things have 0 curl? A gradient has 0 curl. So we're going to say, here's where we start defining more things about A. We can say that E plus j omega A must be equal to the gradient of something. And we're going to name it minus the gradient of a scalar electric potential. Now this is cool because here, if you just have E and not j omega A, E is already the gradient of a scalar electric potential, the voltage. In a DC situation, the j omega A term goes away because omega, the frequency, would be 0. In which case, for DC, E is already minus the gradient of the scalar electric potential. So we're just sort of generalizing this to a time-varying case. So if we take that back and we put that back into what we were doing with Ampere's law before, now we're going to have same left-hand side as before. Gradient of the divergence of A minus Laplacian of A equals mu j plus this new thing that we're going to substitute in for E. So we had j omega mu epsilon times those two terms in place of E. So minus the gradient of the electric scalar potential minus j omega A. The next thing we do is multiply out j omega mu epsilon times j omega A. We're going to put that term and this Laplacian term both on the right-hand side. So some stuff is going to equal to Laplacian A plus omega squared mu epsilon A. Oh, hey, that's the square of the wave number. That's a k squared right there. You've met the wave number before in your electromagnetics course, where k is omega square root of mu epsilon. And then on the left-hand side, what do we have? We've got minus mu j plus the gradient of the divergence of A plus the gradient of j omega mu epsilon times that scalar electric potential. Well, we never specified the divergence of A. What if we just make it so that those two terms cancel out? If we do that, and we are completely allowed to do that because A is not defined until we do. We're defining this thing as a mathematical tool to simplify more calculations later. So if we do that, then now we finally do have a wave equation that only involves A and the current density. And we've got minus mu j equals k squared a plus Laplacian a wave equation. This one is inhomogeneous because it isn't 0 on the other side. There's a source term. But the nice thing is that now our magnetic vector potential depends in a simple way on the current. In fact, I'm not going to actually derive this for you, but I'm going to tell you what the solution for this equation is. If you want to know how to solve equations like this, take your differential equations course. But the solutions for this are in spherical coordinates, that the magnetic vector potential at some observation point r is equal to mu over 4 pi, some nice constant terms, times a volume integral over the extent of our sources times a phase term divided by a geometric space loss term